This tutorial is brought to you by PE Prep Engine. Free study guides and practice questions at peprepengine.com.
Week 3, Lesson 8, Bolt Torque Requirements. The last two lessons found the proof load a bolt can carry and set a preload as a fraction of it. But on the shop floor, you can't reach into a joint and dial in a preload. You tighten the bolt to a target torque and trust that torque to produce the tension you want. This lesson closes that loop. It shows how the tightening torque relates to preload through one clean formula, how the surface condition of the bolt swings the answer by nearly a factor of 2, and how the whole chain runs from the thread tables straight to a number on a torque wrench. Here are the two problems. A 1/2-inch 13 grade 5 bolt in a reused lubricated connection, and an M16 class 8.8 bolt in a permanent zinc-plated connection. For each, take the proof load you already found in Lesson 6, scale it to a preload, and turn that preload into a tightening torque. There's no new load lookup. Both proof loads are Lesson 6's anchors. The only fresh inputs are the reuse fraction and the surface finish factor. Concept 1. Torque is a proxy for preload. There's no gauge that reads a bolt's tension directly, so you tighten to a torque and trust it to produce the preload you want. The catch is that most of the torque you apply never becomes tension. It's eaten by friction under the head and in the threads. The torque coefficient rolls all of that friction into a single number. A clean, dry bolt has high friction and a high coefficient. A lubricated bolt has low friction and a low one. For the very same target preload, the lubricated bolt needs far less torque, because less of it is wasted. That's exactly why a torque spec is meaningless unless it names the bolt's condition. Concept 2. Preload is a fraction of proof load. You never pull a bolt all the way to its proof load. You leave a margin. The handbook sets the preload at a fixed fraction, 90% of proof load for a permanent connection, one that's assembled once and never loosened, and 75% for a connection that will be taken apart and reused. The permanent joint can be pulled up tighter for maximum clamp. The reused joint backs off to leave room for the wear and scatter of repeated tightening. You choose the fraction by how the joint is used, not by the bolt itself. Concept 3. The whole lesson is one chain. Nothing is derived. The skill is running 4 steps in order. The Lesson 6 tables give the tensile stress area and the proof strength. Multiply those for the scale the proof load by the reuse fraction for the preload. Multiply the preload by the torque coefficient and the bolt diameter for the torque. Each arrow is a single multiply, and each link is a different quantity. Proof load and preload are forces. Torque is a torque. Keep them straight, and the answer just falls out. Setup. Part 1. The torque equation. The whole lesson lives in one handbook subsection. The tightening torque is the torque coefficient times the preload times the bolt diameter. The preload is the reuse fraction times the proof load, and the proof load is the tensile stress area times the proof strength, straight from Lesson 6. There's also a fallback, proof strength as 85% of yield, but that's only for materials with no tabulated proof value. Both our bolts read proof strength directly from the tables. One thing to lock in now. The diameter here is the nominal diameter, never the pitch or minor. Setup. Part 2. The surface finish factor. It comes from a short table keyed entirely to the bolt's condition, from a non-plated black finish at the top, down to special anti-seize and grip nuts at the bottom. Read it by condition, never by grade. Because torque scales directly with the coefficient at a fixed preload, a dry black bolt needs roughly 1.7 times the torque of the very same bolt, lubricated. That spread is the single biggest distractor on a torque problem. Miss the condition, and every answer choice will look reasonable. Our two bolts are lubricated and zinc-plated. Solve Problem 1. The 1/2-inch grade 5, reused and lubricated. Take the proof load from Lesson 6. Reused, so the preload is 75% of it. Lubricated, so the coefficient is 0.18, and the diameter is the nominal 1/2-inch. Multiply through, and the torque is about 815 inch-pounds, or roughly 68 in the foot-pounds a wrench actually reads. Solve. Problem 2. The M16 class 8.8, permanent and zinc-plated. Take its proof load from Lesson 6. Permanent, so the preload is 90% of it. Zinc-plated, so the coefficient is 0.20, and the diameter is 16 millimeters. Multiply through in consistent metric units, and the torque is about 271 newton-meters. The handbook writes the formula in inch-pounds, but the coefficient is dimensionless, so the same equation works in any consistent system. Feed it newtons and meters, and it hands back newton-meters. Traps. 5 ways this bites. 1. The wrong coefficient for the condition. Lubricated versus dry black is nearly double the torque at the same preload, and it's the top distractor. 2. The wrong reuse fraction. 75 for reused, 90 for permanent, chosen by how the joint is used. 3. The wrong diameter. Use the nominal, never the pitch or minor. 4. Inch-pounds versus foot-pounds. The handbook gives inch-pounds, so divide by 12 for the wrench. 5. Don't mix the links. Proof load and preload are forces, torque is a torque, and you must scale by the reuse fraction before you ever reach the torque formula. Quick recall. Proof load is tensile stress area times proof strength. Preload is the reuse fraction times proof load. 75% reused, 90% permanent. Torque is the coefficient times preload times the nominal diameter. Pick the coefficient by the bolt's condition, from black finish at the high end down to lubricated. Watch the units. Divide inch-pounds by 12 for foot-pounds, or work in consistent metric for newton-meters. Remember the 2 worked answers, about 68 foot-pounds for the half-inch grade 5, and about 271 newton-meters for the M16. Next up, Lesson 9, Adhesives and Bonding. This lesson closed the bolted joint arc, proof load, preload, and the torque that produces it. But not every joint uses a bolt or a weld. Many are bonded, and adhesives play by different rules. Lesson 9 looks at how a bonded joint carries load across its area, why lap joints are built for shear instead of peel, and what the handbook says about their strength. A different attachment, a different failure mode. Everything's at peprepengine.com. Cheat sheet, work solution, and a quiz attached here.
The full study guide, with every equation and common exam trap, is free at peprepengine.com. Link in the description. Machine design, HVAC, structural, civil, and electrical series are coming soon. Subscribe so you don't miss them.